But today we are discussing about Unit 8 integral domains concepts. Definition. Let triplet R plus star be a ring. Be a ring. Be a ring. A non-zero element small a non-zero element A. Page number 163. 163 page. A in R is called a zero divisor. Is called a zero divisor. Called a zero divisor. If there exists B is not equal to 0. If there exists B is not equal to 0 in R such that means such that AB equal to 0, that equal to BA equal to BA. No. In a commutative ring, there is no distinction between commutative ring. Commutative ring. There is no distinction. There is no distinction between left and right. No distinction. Between left and right zero divisions. Between left and right. Left and right zero divisors. Second one. A ring R has no zero divisors. A ring R has no zero divisors. No zero divisors. If and only if A comma B belongs to R. AB equal to 0. AB equal to 0. That implies either A equal to 0, A equal to 0, or B equal to 0. Next page. Examples. Example. In a ring, in a ring, a ring. Z6 addition over addition 6 multiplication star on 6. Who is the zero divisor? Who is the zero divisor? Who is the zero divisor? Because 2 is not equal to 0. 2 is not equal to 0. 2 is not equal to 0. And 2 star 2 star 6 to 3 equal to 0. And 3 is not equal to 0 in Z6. In integer Z6. For the same reason, 3 is zero divisor in Z6. Example 2. So in a ring, in a ring, in a ring, Z comma plus comma. There is no zero divisors. There is no zero divisors. No zero divisors. There is no zero divisors. Because for any or because for any 0 is not equal to A, it belongs to Z. And 0 equal to 0 equal to B. This belongs to Z. So AB is not equal to 0. So using these definitions, we prove one theorem, page number 163. Same page number, theorem. Statement. Ring R has no zero divisors. Ring R has a ring R has no zero divisors. No zero divisors. If and only if cancellation law holds in R. If and only if cancellation law holds cancellation law holds in R. Cancellation law holds in R. Proof. Next page. Proof. Let R has no zero divisors. Let R has no zero divisors. Let ABC belongs to, let ABC belongs to capital R. We such that ST means such that A is not equal to 0, is not equal. Then AB equal to AC equal to, it implies AB minus AC. That equal to A you are taking common means B minus C. That implies B minus C equal to 0. B minus C equal to 0. That implies B equal to C. B equal to C. Since A is not equal to A, A is not equal to A. Similarly, we can prove. Similarly, we can prove. Similarly, we can prove. A is not equal to 0. That means BA equal to CA. CA. That implies B equal to C. B equal to C. So the cancellation law holds in R. Therefore, the cancellation law holds in R. Holds in R. Cancellation law holds in R. If possible, suppose that. If possible, suppose that. Possible, suppose that. Cancellation law holds in R. Cancellation law. Holds in R. Holds in R. Conversely, suppose that. So if possible, A belongs to R. If possible, let A comma B belongs to R. A comma B belongs to R. Such that A is not equal to 0, B is not equal to 0. And AB equal to 0. AB equal to 0. Now, AB equal to 0. That implies AB equal to A into 0. That equal to B equal to 0. It implies B equal to 0. So left cancellation law. This is by left cancellation law. Left cancellation. This is a contradiction. This is a contradiction. This is a contradiction. A is not equal to 0. That is, A is not equal to 0. B is not equal to 0. A is not equal to 0. B is not equal to 0. And AB equal to 0. And AB equal to 0. This is not true on R. Is not true or R has no zero divisors. Therefore, R has no zero divisors. R has no zero divisors. Next definition. Next definition. This theorem is important for convenience. A non-trivial commutative ring. Non-trivial commutative ring. Non-trivial commutative ring. With identity is called. With identity identity is called. Identity is called. Identity is called an integral domain. An integral domain. An integral domain. If it has no zero divisors, if it has no zero divisors, no zero divisors. Examples. Example. The ring Z has integer. The ring Z has ring Z has integers is an integral domain of integers integers is an integral domain is an integral domain second one. For any integers for any integers n is greater than or equal to 1, greater than 1, it is Zn is an integral domain is an integral domain is an integral domain if and only if n is a prime number. If and only if n is a prime number. N is a prime number. This follows since n is a prime number if and only if relatively prime with any positive integer less than n. Using these definitions, we prove one theorem. Page number 166. Theorem. Let R be a non-trivial commutative ring with identity. Let R be a non-trivial commutative ring. Trivial commutative ring. Commutative ring. Non-trivial commutative ring with identity. Then the following are equivalent. Then the following are equivalent. Following are equivalent. First one. R is an integral domain. Is an integral domain. R is an integral domain. Second, for any A belongs to R, A B equal to 0. For any A comma B belongs to R. That implies A equal to 0 or B equal to 0. A equal to 0 or B equal to 0. Third one, for any ABC belongs to R, belongs to R, AB equal to AC. That implies A equal to 0 or B equal to A equal to 0 or B equal to C. B equal to C. Proof. For 10 marks, most important. So one implies let R be integral domain. Let R be an integral domain. R be an integral domain. Then there are no zero divisors in R. Then there are then there are no zero divisors in R. No zero divisors in R. For any A belongs to R, A comma B belongs to R. If A B equal to 0, A B equal to 0, and A is not equal to 0, and A is not equal to 0, then B equal to 0, then B equal to 0. Otherwise, A becomes a zero divisor. Therefore, AB equal to 0, AB equal to 0, then A equal to 0, or B equal to 0, B equal to 0. Let ABC belongs to R. ABC belongs to R. Such that AB equal to AC. ST means such that AB equal to AC. AB equal to AC. That implies AB minus AC equal to 0. That implies take A is common. B minus C equal to 0. 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 And hence by 2. Hence by 2. Second bit. A equal to 0 or B minus C equal to 0. A equal to 0 or B minus C equal to 0. B minus C equal to 0. That means A equal to 0, B equal to C. Okay. So third implies third property implies also. Let AB equal to AC. AB AB equal to AC. AB equal to AC. Nice. AC. Implies A equal to 0. A equal to 0 or B equal to C. To prove that R is an integral domain, R is an integral domain. Integral domain. R is an integral domain. We have to prove that R has no zero divisors. We need to prove that R has no zero divisors. R has no zero divisors. R has no zero divisors. Let A is a non-divisor in R. A is a non-zero divisor in R. Non-zero divisor. Then A is not equal to 0. Then A is not equal to 0. A is not equal to 0. AB and AB equal to 0. AB equal to 0. For some 0 is not equal to B, it belongs to capital R. Now AB equal to 0. AB equal to 0. That equal to A into 0. From A is not equal to 0. And B is not equal to 0. B is not equal to 0. This contradicts the third. This contradicts the third. This contradicts third. R has no zero divisors. Therefore, R has no zero divisors. Hence proof. Hence proof. Fields definition. Fields. Fields definition. Fields definition. A commutative ring triplet. A commutative ring. A commutative ring. Commutative ring. A commutative ring. Triplet means R plus star. Is called a field. Is called a field. It's called a field. If the set of non-zero elements, the set of page number 167, if the set of non-zero elements form a group, non-zero elements form a group under the multiplication in R. Under the multiplication in R. Under the multiplication in R. That is called field. Examples. EGS means examples. The set Q of all rational numbers set Q of all rational numbers set Q of all rational numbers is a field. A field. Because Q plus star is a commutative ring with identity. Is a commutative ring identity. Commutative ring with identity. Commutative ring with identity. And every non-zero elements in Q. Every non-zero elements where non-zero element in Q means set of rational numbers. as multiplicative inverse. As multiplicative inverse. Multiplicative inverse. Second, the set Z of all integers. The set Z means integers. All integers. All integers. Z of all integers is not a field. Not a field. Not a field. Because all non-zero elements of Z. Because all non-zero elements of Z elements of Z, non-zero elements of Z are not units. Are not units. That is, every non-zero element of Z, every non-zero element of Z non-zero element of Z, non-zero element of Z has no multiplicative inverse. Z has no multiplicative inverse. Multiplicative inverse. That's why it is not a field. First one is a field. So one more definition. A ring, ring R plus star is a division ring, is called division ring. Division ring. Division ring. Or skew field. Or skew field. Or skew field. If the set of non-zero elements, if the set of non-zero elements, zero elements, non-zero elements of R is a group. R is a group. R is a group. Under multiplication. Under multiplication. Under multiplication. Examples. Example. A triplet Z plus star is a division ring. Triplet Z plus star is a division ring. Division ring. Division ring. Two plus and R plus star are division rings. Division division rings. So using this definition, we prove a theorem that is 10 marks important. Page number 167. Zero. Every field is an integral domain.
Excuse me, sir.
Is
Sir,
an integral domain. Page number 167.
सर बुक्स में इज ए नॉट डिवीजन रिंग लिखा है.
No?
एग्जाम्पल 1
Example 1, thus.
इज नॉट ए डिवीजन रिंग बुक्स में.
It is not a division ring. That means the set of non-zero elements in R under multiplication. So Z means
No, sir, you wrote is a division ring. Z plus and multiply sign in a division ring you wrote the triplet.
not a, that is not, I wrote wrong. Is not a division ring, because in set of integers both positive negative and together with zero na. So multiplication to inverse does not exist. Zero. 1 by 0 means infinity will go na. I wrote wrong. You have to correct it. Is not a division ring. Right. Thank you. Next theorem. Every field is an integral domain. Every field is an integral domain. Integral domain. But the converse need not be true. But the converse need not be true. Need not be true. Proof. Let R be a field triplet. Let triplet R be a field. Be a field. Be a field. R is commutative ring with identity. Then R is commutative ring. Ring with identity. Identity ring with identity, in which every non-zero element has multiplicative inverse. In which every non-zero elements, every non-zero elements has multiplicative inverse. Has multiplicative inverse. Multiplicative inverse. Has multiplicative inverse. So it is enough to prove that there are no zero divisors. Is enough to prove that there are no zero divisors in R. There are no zero divisors in R. There is no divisors in R. Let A B belongs to let A comma B belongs to R. If A is not equal to 0, such that AB equal to 0. ST means such that AB equal to 0. Then A is not equal to 0. A is not equal to 0. That implies A inverse. That implies A inverse exists. A inverse exists. A inverse exists. A comma A inverse. That equal to A inverse into A. That equal to 1. Now AB equal to 0. AB equal to 0. That implies A inverse AB. A inverse AB. That equal to A inverse A. A inverse A inverse 0. A inverse into 0. That equal to A inverse A into G. A inverse A inverse A into B. That equal to 0. That implies 1 into B. That equal to 0. That implies B equal to 0. Similarly, let AB equal to 0. Let AB equal to 0. AB equal to 0. With B is not equal to 0. With B is not equal to 0. Then B inverse exists. Then B inverse exists. B inverse exists. And B inverse exists. And B into B inverse. That equal to B inverse into B. That equal to 1. Equal to 1. Then AB equal to 0. Then AB equal to 0. That implies AB equal to 0. That implies AB B inverse B inverse. That equal to 0 into B inverse to B inverse. 0 into B. That implies 0 into B inverse. That implies A into B inverse. That equal to 0. B into B inverse. B inverse. That equal to 0. That implies A into 1. That equal to 0. That implies A equal to 0. A equal to 0. So in a field R, R, AB equal to 0. AB equal to 0. that implies A equal to 0 or B equal to 0. B equal to 0. Thus thus R has, thus R has no zero divisors. No zero divisors. R has no zero divisors. And hence R. And hence R. And hence R is an integral domain. Is an integral domain. R has integral domain. So the converse of this result need not be true. The converse of this result need not be true. Need not be true. Need not be true. We can exhibit integral domain. We can exhibit integral domain. Integral domain. Integral domain, which is not are not field, which are not field. They are not field. Which are not field. They are not fields. Consider the ring Z. For example, consider the ring Z as integers with the usual operations of addition and multiplication. Thus, this is an integral domain, but it is not field because no integer except 1 and -1 has multiplicative inverse in Z. Even though every integral domain is not a field, we have, however, following the result with respect to the finite integral domain. So till here it is enough. Hence problem. Next. One more 10 marks theorem is there. Page number 168. Yeah. 10 marks. Prove that every finite integral domain is a field. Prove that every finite integral domain. Finite integral domain is a field. A field. Let R plus let R triplet be a finite integral domain. Finite integral domain. Integral domain. Then it is non-trivial commutative ring. Then it is non-trivial commutative ring. Commutative ring. non-trivial completed line. With multiplication identity 1. With the multiplication 2. With multiplicative inverse. Mi means multiplicative inverse consider. Multiplicative identity 1 is not equal to 0. Since R is a given to be finite. Since R is here given finite. So R minus 0. So it is R minus 0. Also, if if A Aj that equal to A Ak, then Aj equal to Ak, Aj equal to Ak, Aj equal to Ak. Therefore, AA1, comma, AA2, etc. is a subring of R minus U of R minus U has exactly n elements. Has exactly n elements. Exactly n elements. Thus, R minus 0 that equal to AA1, AA2, etc. AAN. AAN. Since 1 belongs to R minus 0, R minus 0, 1 equal to AA1, AA for all j equal to 1, 2, 3. There is multiplicative inverse in R. There is Mi, means multiplicative inverse in R minus 0. Thus, R minus 0 is a group under multiplication. GB means group under multiplication. It means multiplication. And hence, triplet R star is a field. Hence proved. Next. Page number 169. 169. Theorem number 8.3.7. Do it as homework. And page number 173. Page number 173. Now work out example 8.4.1. 8.4.1. Homework. Important for 10 marks. 10 marks theory question. Next. 8.4.2. 8.4.2. Do it as homework. These three theorems are do it as homework. Important for 10 minutes. So time up and leaving. Okay, these three theorems are do it as homework. Time up. I'm leaving. Thank you.
Sir, are these homework problems important?
Three theorems, 8.4.1, 8.4.2, worked out examples, page number 173 and 174.
How
10
much marks do they contain, sir? Like weightage?
Hmm?
What is the weight of these questions? Like if they
10
come in
marks, 10
exam?
marks.